time to get your calculators out. Let's look at average atomic mass. Also, periodic table might be handy. Here's the deal. When you look at the periodic table, people always ask this, why are we rounding those masses? You know, we filled out this big data table. We've got protons, neutrons, electrons, all this good stuff. Why do we have to round the masses? You know, why are they decimals and not whole number masses on the periodic table? We're rounding them anyway. Why aren't they reported as whole numbers? Gosh, that's a good question. You were thinking it, weren't you? Here's the deal. If I look at the periodic table, and let's say I'm checking hydrogen, for example. Hydrogen. The periodic table I'm looking at has a mass of 1.00794. And remember, these are AMUs, not grams. Hydrogen does not have a mass of 1 gram per atom. That would be crazy. I mean, it's really darn close to 1, isn't it? It's almost 1. We're going to round it to 1. So where does that 0.00794 come from? The fact that it's a weighted average atomic mass. This mass on the periodic table takes into consideration two things. Number one, the abundance of all the existing isotopes. And number two, the mass of those in particular isotopes. So for example, hydrogen has 3 common isotopes. Hydrogen mass 1, hydrogen mass 2, hydrogen mass 3. Most common, most stable isotopes. Now, it's not just a flat-out average. Here are the 3 isotopes. If I add 1 plus 2 plus 3 and divide by 2 and just take an average mass, we would be saying that hydrogen's mass is 2. And it's not. It's a weighted average. It also takes into consideration the abundance of each isotope. So, for example, like over 99% of all the hydrogen on the face of this earth is hydrogen 1. Just a very small fraction of the hydrogen atoms are mass 2 and 3. So this might be like, I don't know, about 0.7%, and maybe this is about 0.3%. So it adds up to 100% of all the isotopes. Oh, do you see where I'm going with this? 99% of all the isotopes are mass 1. So the mass number that you see on the periodic table is darn close to 1. It's going to be closest to the most stable and the most abundant. So maybe we'll make a little note. This is the most stable. Isotope, and it has the greatest abundance. In nature. Oh yeah. So then that's why the weighted mass on the periodic table is darn close to 1. The 0.00794 is from the calculated weighted average. So the mass on the periodic table is just a hair greater than 1, because there's a very small fraction of hydrogen atoms that have a mass that's a little bit greater than 1. Here's how it's calculated. Alright, so you pull out your calculator, and you'd be given data kind of like this. There is an element, and it has the following isotopes. There's a mass of 14.2 AMU, 14.0, and 16.8. What is the weighted average mass of the element? Now we're also given the percent abundance. So 50%, most of these isotopes are the heaviest version, the 16.8. To do this calculation and find the weight that would be listed on the periodic table, all we got to do is this. Take the percent as a decimal, 0.30, and multiply by that mass, 14.2 AMU. And then we do the same thing with all of them. 0.2 times 14.0 atomic mass units, and 0.5 times 16.8. And then you just add them all up, plug them in your calculator. Oh, well, that's not so bad, is it? Okay, now for figures and decimal spots, for sig figs, all that good stuff, I usually say match the data that's given. So the data given, all those masses have 3 sig figs. So let's report 3 sig figs in our calculated mass. So I'm going to plug this in my calculator. 0.30 times 14.2. I'm going to add 0.20 times 14 plus 0.5 times 16.8. And I'm going to round it to 3 sig figs. I'm going to try to match the data given and say 15.5 AMU. That's the mass number that would appear on the periodic table. And now look at the data. I would expect that this number should be like closer to 16 than 14. 50% of the isotopes are that heaviest version. Now the other 50% are a little lighter, so it makes sense that my weighted average mass is a little bit less than like 16, somewhere in that ballpark. So when you're doing these, let's say it's a multiple choice question, you might be able to weed out some answers that don't make any sense. The weighted mass cannot be greater than the heaviest isotope. It cannot be less than the lightest isotope. It should be closest to the one that's most abundant. This is fun. Let's try another one. Alright. An element has 2 isotopes with the following masses. And again, they'll always give you the abundance. What is the weighted average mass? The biggest mistake I see is that people just forget that you need to multiply the percent as a decimal. So you're going to use this as 0.95 times 86. And then we're going to add we got to move the decimal, 0.5 times 91. Plug it in your calculator. This time the masses given are all whole numbers. So I'll just round this to the nearest whole number. And interesting. Okay, so on my calculator, I'm looking at like about 86.25. But if I round that to the nearest whole number, I might just leave 86. 95% of the isotopes have a mass of 86. It's by far the most abundant. A very, very small fraction have a mass that's slightly greater, which is why on my calculator I get a mass that is slightly greater than 86, 86.25. But for sig figs, if I leave my weighted mass to match the data given, we'll go back to 86. A very small fraction of the atoms are a little bit heavier. So these become pretty easy after a while. The biggest mistake is that people just sometimes forget to move the decimal spot correctly. So I would suggest at this point, pause the video, pull out your calculator, and try number 3 and 4. Then bring it back on and see if you're getting the right answer. Hopefully these are a piece of cake. Alright, so let's check these over. Let's see if you got them right. I have 3 isotopes. I'm going to move the decimal spot 2 places and use these as decimals. 0.846 times 104.3 atomic mass units. 0.104 times 1/5 18.5 AMU. And now this 6%, I still have to move that 2 places. So this should look like 0.06 times 120.0 AMUs. Plug in your calculator, add them all up. All the data has 1, 2, 3, 4 significant figures, so I will leave 4. We'll let our calculated mass match the data given. So I'm going to plug this in my calculator and report 107.4 AMU. And then I can double check and see if this answer is reasonable. So about like 85% of the isotopes have a mass of 104. The other approximately 15% are a little bit heavier. So does it make sense that my weighted mass is a little bit greater than 104? Yeah, 107 seems good. That seems reasonable. And the last one. Again, we have 3 isotopes. Let's plug this in our calculator. 0.241 times 75.23 AMUs. 0.487 times 74.61. These masses are all pretty close, aren't they? And 0.272 times 75.20 AMU. This element has 3 stable isotopes. We have their masses, we have their percent abundance in nature. We plug this in our calculator, we add it up. Oh, let's see here. This time they have 4 sig figs, 2 decimal places, so I'll leave the same. I'll plug this in my calculator and say 74.9199, let's go 92 AMUs. Does this make sense? Yeah, I'd say about 50% of the isotopes have a mass darn close to 75, 74.6. The rest of them are a little bit heavier. So yes, it makes sense then that my weighted mass is a little bit greater than 74.6. Now the other fun thing that this one asks, what is the identity of the element? So all I got to do is look on the periodic table and find the element with a mass that's the closest. Now mass numbers do increase. They don't increase by the exact same increment like atomic numbers, they just increase by 1. But I would say this is probably closest.
Cassie Amo, please call 6506.
To arsenic.
Cassie 6506.
That's how they get the masses that appear on the periodic table. They're weighted averages that take into consideration all the different isotopes and their abundance in nature. So often, when we round the masses to a whole number, we're usually rounding them closest to the most abundant isotope.
Dorothy, please dial 6506.